So it's a measure of the breadth and the depth of Tony's work in physics that I couldn't decide what to speak on in this meeting. The two choices I had in mind were diffusion at absolute zero or the meaning of causality in relativistic quantum theory, which you can see is what it's about today. The first topic relates closely to some work that Tony actually mentioned this morning, the Caldera-Leggett model for damping. What we found is using the fluctuation dissipation theorem, a sort of logarithmic spreading at very low temperature, and the experiments to test it are now in progress here at RRI. The second talk is more conceptual, or especially after Tony's recounting of his history in physics today, I should say it's also philosophical, which maybe will appeal to the early Tony. And as I said, it has to do with causality. Here are some partial references. What I'm going to say today is not actually published anywhere in full. So relativistic, we don't need this. Skip the abstract. Okay. So causal relationships are important in many branches of physics. Quantum field theory, classical general relativity, obviously, in quantum foundations. And furthermore, causality appeals to us as a basic scientific category. And despite all of that, cause and effect lack a clear definition in the quantum world. One might hope, people don't even agree whether the EPR-like correlation should be regarded as acausal, non-local, or both. One might hope that a better understanding of causality would be a step towards deciphering the quantum formalism, and also an important clue towards quantum gravity, especially in relation with the approach to quantum gravity that some of us are working on, which is based on causal relationships called causal sets. Now, even classically, the concept of cause and effect is elusive. In quantum field theory, because basically physics rather deals with correlations than causation directly, in quantum field theory, it's still harder to give cause and effect meaning because it concerns basically events, whereas field operators are not events. In an operator formulation of quantum mechanics, the only true event is a measurement which goes along with this ensuing quote-unquote collapse of the state vector. But measurement and collapse rely on external observers, which in particular for quantum gravity is a bad thing, and philosophically speaking for many people as well. However, in terms of histories, for example, particle trajectories, events can be delineated, which would be also familiar to people working on Bohmian approaches. It thus seems worthwhile to explore questions of causality and locality in connection with the histories-based formulation of quantum dynamics. Now, what I've underlined here, quantum measure theory, which is a form of the path integral that I'll introduce more fully later, is such a framework, a histories-based framework, and within it, an event has a meaning as a set of histories, which is the same terminology that's used in probability theory more generally. This talk will explore causality and locality in connection with EPR-like correlations. I'll consider only particles and their trajectories with no bringing in of external observers or agents. And the kind of events we will consider would be, you can think of this picture, sort of schematic of an EPR-like experiment with a source and two, say, Stern-Gerlach or whatever they may be, analyzers, and ultimately the particle will emerge either in the upper beam or the lower beam, U or D I've called them, and the events that we're interested in are precisely those things, the particles emerging in either this beam or this beam, and the same for this particle. Now, the kind of events we'll be interested in are, first of all, the ones I just mentioned. A particular example of an event is the particle on the left emerges in the upper beam. That's an event. But another example of an event, remember an event is a set of histories, another example of an event is the correlation event, which is in red, or whatever this is, magenta here, which is that the left and right particles emerge in corresponding beams. So I'm not telling you where they emerge, but they either both emerge in U or they both emerge in D. And that's an event of correlation, but it's not a locally meaningful event. So that's sort of the framework we'll be discussing these causality and locality in. Now, causality and locality are two basic principles which, as is well known, help to shape classical physics. However, the words don't necessarily mean the same to everyone, especially in the context of quantum foundations. So let me define them as I'm going to use them. By causality, and more specifically by relativistic causality, I mean the principle that no cause can act outside its future light cone. By locality, I mean that no cause can act outside its immediate space-time neighborhood. So these are a priori very different things. So to illustrate this, and also to give the space-time context for this EPR-like experiment, look at the second figure down here. So we have two regions. These are space-time regions. That's in which the place and time during which this analyzer is active is encountering the particle. By the way, I should have said, or I should say now, that I wrote here A or A prime. Those are representing two possible settings of the analyzer, and similarly B or B prime. But the space-time regions here are the same, A and B, and there will be always a past region, which is somehow supposed to be the preparation, or whatever it is that's responsible for the correlation between A and B. People sometimes consider two different cases. I'm not going to dwell or worry about which one until right at the end. Sometimes they say that the common cause, as it's sometimes called, should be in the common past of A and B, the points which are to the past of both. Sometimes they say in the union of the two pasts, which is this bigger region, Z. But the important thing is that the preparation, or the cause for the correlation, should be in region Z, and the correlation is between regions A and B. Now, the kind of correlations that show up in the quantum world is generally agreed by most workers that they contradict what Bell called local causality. Some of the strongest original argument is the Alan Ster's version of the Koch-Specker paradox. Other ones that you may be familiar with, are the GHZ and the Hardy experiments. So if we give up, so we can't have both locality and causality, apparently. Certainly in the quantum formalism that we have, it doesn't have them both. But if we give up locality, as arguably we must do for quantum gravity anyway, that's a separate argument, but I would argue that quantum gravity cannot really be local. Remember, by locality I mean no action at a distance. If we give up locality, then I think there is really no conflict with causality in these correlations. And the reason is that a preparation event in the region Z here can cause a correlation event. It must do so non-locally in the region, any region to its future, and A union V is a region to the future of Z. It can cause the correlation event to happen without necessarily causing any individual event, either in region A or B separately. And then we'll see that although we have to sacrifice locality, I believe, a certain degree of locality, or maybe it's better called separability, seems to remain in the known relativistic quantum series, of which quantum field theory is the most important example, of course. So this is all at a very general level. Now, I want to consider what some of these things might mean, what would count as a cause and a locally causal influence in the context of the CHS inequalities, which are the fancy or nicer version of the Bell inequalities, and specifically of Arthur Fine's derivation of these inequalities. So let's briefly review how his derivation goes. We have two possible settings, as I've said before, here, A or A prime, B or B prime. So 4 possible pairs of settings. And for each one, we can have 4 sets of events that we're interested in, depending on where the particles emerge. So I'll call A the left-handed, either U or D, depending on whether the left-handed particle emerged either in the upper or lower beam. And similarly for B, A prime and B prime are the same events with the different settings, with the prime settings, and so on. Now, for each of these sets of events, we have a set of probabilities. So if with both unprimed settings, then we have a P of AB, which is 4 probabilities, and so on. So that's the setup. Now, how does local causality imply the CHSH inequalities? For lack of time, I can't give all the details, but I'll highlight the steps that are important for the argument I'm going to make. First of all, we observe that local causality, you have to interpret what it means, but it's argued to entail factorization. Factorization has other names. It's called, often in the philosophical literature, screening off. Sometimes it's called Reichenbach's common cause principle. What it means in practice here is that the probabilities, the joint probabilities of A, B, and Z, these being events in the regions big A, big B, and big Z, are related to the individual separate probabilities in this way, by this equation, which if P of Z is not 0, we can divide through by P of Z squared, and you can read this equation to say that the conditional probability for A and B given Z is just the product of the conditional probability for A given Z times the conditional probability of B given Z, where Z is supposed to count as any full specification of the history in the past region Z. The second thing, which I will show the derivation of, is that if this factorization implies what I'll call patching. Patching will be a key concept for this talk. And what patching means is that these 4 probability distributions can be all put together into one single probability distribution, as if you could do all the settings at once and have probabilities for the outcomes, of which these individual ones are the marginals. That I'll prove that and show the proof in a second. Then it's a short thing, but it's a little too long to have time for. One can prove that when there is a joint probability distribution, one derives the CHSH inequalities, which are the things that are experimentally contradicted. Okay. So if we put all these things together, these implications, we have that screening off, which was a manifestation of local causality, implies patching, the existence of a joint probability measure. I should stress, I wrote it, but I didn't stress it, we're now doing classical physics. The Bell inequalities are, of course, defined in terms of classical physics, classical probabilities. So the screening off implies the existence of a joint probability measure, and that implies the CHSH inequality. So it's kind of a 2-step argument. How the first argument works is as follows. Remember, patching means to combine these 4 probability distributions into one of which they are marginals. And you do that by making the following, Fahn does this by making the following simple ansatz. That you just take basically this joint probability that you're trying to construct to be a product of all the individual probabilities. After bringing this Z, this past history, into play and normalize it appropriately, so you've now defined the joint probabilities. And if you want this, if you don't want Z anymore, it just is an auxiliary, you just sum over it to get a probability distribution for A, B, A prime and B prime. So the important thing is that when the probability is factorized in the way that I showed before, this way, then there's a simple ansatz to get patching. This suggests, and that was coming from a causal and actually a local and causal hypothesis, which was sorry for this, but I'm usually used to using the other computer. So that was this screening off, which was coming from, meant to be a manifestation of local causality. So this suggests that if we can find a quantal analog of local causality, it would imply a quantal version of patching. I'll say in a moment exactly what a quantal version of patching would mean. One side remark here, well, maybe I'll just skip, is that this condition of patchability has been considered in other contexts, actually closely related, and if you assume that and not all of quantum theory, you get what Tony Yassin and others call also almost quantum correlations. Now, to explain what patching can mean in the quantum realm, I have to go back and define a version of the path integral, which I referred to before, which is called quantum measure theory. In this version, instead of having probabilities like the probability of A and B here, we have what's called a quantum measure, which is a generalization of a probability of the same event, and correspondingly Schwinger amplitudes, which are amplitudes for pairs of events, where there's a requirement on this matrix, should be positive Hermitian matrix, additive in each argument. When this is true, then the relation between the quantum measure and this D, which is called the decoherence functional, is that the quantum measure is just the diagonal element of the decoherence functional, which is basically a sum over all the histories making up the event E of this, all interference terms, amplitude, including self-interference between the two histories, as given by D. A couple of remarks. First of all, this mu of E comes from a double path integral. That's what you could regard this, and it is usually realized as a double path integral. It's just a double sum over histories. Furthermore, this measure reduces to an ordinary probability when E is a special kind of an event, namely an instrument event. That's a restatement of the Born rule, basically. So if we assume the Born rule, then we're saying that it can be interpreted as an ordinary probability. In general, it's not. And finally, it satisfies a three-slit sum rule, which expresses the absence of third or higher order interference. This also has close connections with RRI, especially through Urvashi, who did the experiment that looked for higher order interference. So how do I? Now, now I've defined inadequately, but I've defined quantum measure theory. And the question is now, how much of fine scheme can we reproduce in quantum measure theory? Now remember, classically, we had local causality implies screening off, which was the factorization, implies patching, implies CHSH. In quantum mechanics, we know how to do part of this, patching, which now means not a joint probability, but a joint quantum measure, joint in the same sense. That patching implies not the CHS inequalities, but what are called the Tsirelson inequalities. So what one sees here is that the Tsirelson inequalities are, in a precise sense, the quantum analogs of the Bell inequalities. But what we don't know is what to put here. What causality condition would let us fill this scheme in, a la Fine's work, generalized to quantum mechanics? A brief comment is that you could write down, using the decoherence functional, just a naive generalization of this this factorization condition. And if you do that, you could write down, you could try this same ansatz, but it turns out that it doesn't work because, where is it? Turns out it doesn't, unfortunately fails. For one thing, you'd be dividing by 0. There are other problems. So that in itself will not let you lead to patching. So what would lead to patching? So this gets back to the title of the talk. I want to introduce a condition which I'll call persistence of 0, interpreted as a causality criterion, and show that if we assume it plus something a little bit extra, then we do get patching, and we therefore derive, in particular, the Zierelson inequalities for this EPR setup. However, to describe what persistence of 0 means, I have to go a little deeper into quantum measure theory. So I described quantum measure theory in terms of attaching a number, a non-negative real number, in fact, to every event, its generalized probability or quantum probability. What we can also do, thanks to this assumption of positive semi-definites that I referred to, we can, in fact, attach to every event not only a number, but a vector in some Hilbert space. And we do that by interpreting this decoherence functional here as what's sometimes called the Gram matrix. In other words, we assume we can prove that there exist vectors x and y whose inner products match those given by the decoherence functional. Therefore, we attach to every event x a vector, and to every region of space-time, a Hilbert space, which is that spanned by the vectors corresponding to the events that can take place in that region. So, for example, if we had here the event z, little z, whatever it was that we kept referring to before, and the event A, say here, either upper or lower beam emergence, then that's an event in the region of A, together with Z, right? And all those events span a Hilbert space, H, A, Z, and that's a subset of the larger Hilbert space, which is spanned by all the events in every region under consideration. This is what's called, by the way, a vector-valued measure. Now, in terms of the vector value measure, I have to define persistence of 0. And to define that, which I'm going to promote as the missing causality condition, at least as an interesting causality condition, to define what that means, we only need to consider 2 regions. So persistent means persisting from past to future. So consider, for example, region Z and region A. So in relation to those 2 regions, or even better, say this Z and this A here, in relation to that, it says the following. Consider any event in A and a bunch of events in Z and a function and a bunch of coefficients, complex coefficients, psi of Z. Suppose that the sum of these vectors Z with coefficient psi of Z is the 0 vector in the Hilbert space, which means that its quantum measure is 0, or the generalized quantum measure that we can associate to it, which is just Z inner product, it's this vector inner product with itself, is 0. It then follows, according to this hypothesis, or this principle, that the same sum of the events Z and A is also 0. So in other words, a vector which is 0 here, if you then add some extra restriction on the events that go into it by saying that some later event has happened, it remains 0. It probably sounds a little abstruse, but let me mention that it holds automatically in unitary quantum field theory and can be derived from the double pass integral. So I think I'll run rapidly through this, but this is in some sense the most important technical point, that persistence of 0 does imply patching, provided that this Hilbert space associated with the past region is actually the full Hilbert space of the system. The proof comes from the fact that if you have persistence of 0, you can build what are called class operators for the events in A and B, which are operators such that, for example, this vector measure of the event A, B, Z can be gotten from Z, the initial or past events vector, by acting with these two class operators. Now, a priori, so that comes from persistence of zero already, nothing more. However, a priori, this A will map HZ into HAZ because Z refers only to the past region, but AZ refers to the region A as well. Or it also maps HBZ into HBZ for the same reason. But if all of these Hilbert spaces are the same, including for the prime, A prime, B prime, and so on, then we can construe all of our class operators as acting in the single Hilbert space HZ. If they all act in the same Hilbert space, we can form products for all the different settings and all the different outcomes. And so we can form products like A prime or B prime B, different settings here. And therefore, we can make a patching ansatz, which rather resembles the classical one, but is not the same. We define the vector, or according to this ansatz, we make the vectors A prime, B prime, and Z, which we bring in as we did before, just by acting with these operators on Z. Now, unlike the classical case, the answer will depend on the choice of factoring ordering between A and A prime and B prime. But so you'll get a bunch of ansatzes or ansätze, but any ordering will do. Finally, notice that this equality is true in quantum field theory, provided that the region Z contains a Cauchy surface for A and B. That is, provided that A and B lie within what's sometimes called the domain of dependence, or the future causal development of the region Z. So this is one way to fill in the above question marks, and it suggests that persistence of zero has a meaning as, if not the manifestation of relativistic causality, then a manifestation of relativistic causality, which is of an interesting new nature and which is suited to be used in quantum gravity and quantum causal set theory in a way that I can't go into. So let me summarize. I had a kind of coda, but I think I'll skip the coda. So because there won't be time for it. So let me make 3 conclusions, or let me call them tentative conclusions from this discussion, because I'm not saying that this is the last word. I think it's very indicative. In even I gave this talk a couple of months ago, and even my attitude towards some of this thing has changed a little, and probably is still changing. But these are fairly firm, I think. So let me call them tentative conclusions. The first thing is, I'll just read it out. Once you admit that a cause can act non-locally, there's no reason at all. That's the first claim I made. Even classically, there's no reason that it cannot cause a correlation between 2 variables in its future without determining either variable separately. For example, to repeat what I said before, a suitable preparation can cause the correlation event, UU or DD, without causing separately either UU or DD. If this is the right way to think about EPR correlations, then we should conclude that relativistic quantum theory is causal but non-local. So that's the first tentative conclusion. Secondly, the analysis we just went through suggests that persistence of zero is a formal manifestation of causality in the context of the path integral or quantum measure theory. It has in particular, this is the wrong, that's because we had to go to the stick. So this is not quite the most recent version of the talk, unfortunately. But as a special case, it tells you that if some event E cannot happen because its measure vanishes, which in quantum measure theory means that the event is forbidden or precluded, as we say, then neither can any event of the form E and then F. Such a kind of, I call it irreversible preclusion of E, constitutes, as one might say, a formal aspect of the past that the future cannot undo. It's an aspect of it as a causality condition. Notice in this connection that this persistence of zero relationship is very much temporally asymmetric, as one expects of causation. So you try and run it backward, it will be false. So that's the second conclusion. And then finally, if we combine persistence of zero with some further conditions, like the one I mentioned before, that holds when this is a Cauchy surface for these regions A and B, then it also implies patching. It thus leads to a kind of separability of relatively space-like events, and this suggests the third thing, that quantum mechanics is actually not as non-local as it might have been. It is non-local, but it still retains some aspects of causality, of locality, fully causal and only partly local, but only partly non-local. This raises the question, is there some new principle, which I'll just name it separable causality, which lies somewhere between causality and local, the stronger condition of local causality, and which is manifested in relativistic quantum theories and may be then manifested in quantum gravity and an important clue to quantum gravity. And I'll stop there.
Does it mean that the absence of persistence of zero implies breakdown of causality?
That's a good question. In general, I think I don't have a model to give you, but that would be my expectation, that if it was not satisfied, you wouldn't get patching. But actually, whether it's a breakdown of causality is a deeper question. My feeling now, for the reason that I expressed before, is that no set of EPR correlations, no matter what, really could count as a breakdown of causality. Because of what I said, that the preparation event could cause that, could cause the correlation without causing anything separately. So I wouldn't want to necessarily say that it was a breakdown of causality, but it'll certainly it'll move you more, it'll introduce a higher level of non-locality than what we see in standard quantum theories. Some people might be familiar that there's a lot of talk about non-locality being limited in one way or another, and people try to make axioms that'll lead us back to the more ordinary quantum mechanics.